Good morning all, my name is Santhosh Kumar. My subject is image processing. Today my topic is introduction to the Fourier transform and frequency domain. So what is the transform and what is the need? Why transform is needed? So the transform is for better image processing and it is take an account long range correlations in space and conceptual insights in spatial frequency information. So what it means to be smooth, moderate change and fast change. So fast computing, convolution versus multiplication. So here one figure is there. It is the input image. So it is converting and it is a final output image. So what is the final output image between the input and output? So what is happening? So it is an account long range correlations in space and it is a smoothing and moderate change of fast change. So what is the difference means here I am applying fast computation. So that is a convolution versus multiplication. So what is a convolution and what is a multiplication we will discuss. So the alternative representation of sensing. Sensing means here I am using some input camera, like example camera. So the alternative representation of sensing is a camera. So to obtain transformed data as measurement in radiology images. So what is a radiology means? Medical and astrophysics. So it is the inverse transform to recover the image. So the efficient storage and the transmission, energy compaction, pick a few representatives and that is the basics and just store and send the contribution from each basis. So here it is the input image. Okay, I am taking it is the output example. So is it clear? No, we are not satisfied with the output image. Suppose it is the input image. Example I am taking, it is the input image. So from input to output, what is happening? Only 50% of information is there. So remaining 50% we have to capture. So how we are capturing means with the help of Fourier transform and we are taking the input to the output. So some 50% of image is converting to the 100% of image. So how is it possible? So it is, we are using here the transformation technique. So what is a transformation means? To obtain the transformed data and measurement in radiology images. That is a medical and astrophysics. So the inverse transform is recover the image. So here only 50% is there. How it is getting 100% means we are using inverse transform to getting the 100% of the image. So the efficient storage and transmission. So what is how we are storing and what is the efficiency of the image storing means here I am taking the energy compaction and pick a few representatives and just store and send the contribution from each basis. That is a image transformation technique. So what are the image transforms are there? Here there are 4 types of image transforms are there. First one is a orthogonal, sinusoidal, basis function, non-sinusoidal, orthogonal basis function, basic function depending on statistics of input signal and directional transformation. So in this orthogonal, sinusoidal, basic function, there are 4 types are there or majorly we are taking 3 types. So what are the 3 types means? I am taking Fourier transform, discrete cosine transform, discrete sine transform. So these are the 3 types are there. And non-sinusoidal orthogonal basis functions are the 4 types: Haar transform, Walsh transform, Hadamard transform and Slander transform. So these are the 4 types of non-sinusoidal orthogonal basis function. Another basis function depending on statistics of input signal, that is a KL transform and singular value decomposition. And directional transformations are the 4 types: Hawk transform, random transform, Radic transform and contorlet transform. Okay, these are the 4 types. So what are the major uses of transforms we will discuss in that next. So totally what is one means image transforms are 4 types. That is a orthogonal sinusoidal basis function, non-sinusoidal orthogonal basis function depending on statistics of input signal and directional transformation. So in this orthogonal there are 3 types are there: Fourier transform, discrete cosine transform, and a discrete sine transform. In non-sinusoidal, there are four types are there: Haar transform, Walsh transform, Hadamard transform, slant transform. So in this basis function, KL transform and singular value decomposition. These are the two types of basis functions. And the directional transformations are four types: Hawk transform, random transform, Reddick transform, and controllet transform. Okay, these are the types of image transformation. And what is the transformation? What is the definition for the transformation? So a signal can be converted from time domain into the frequency domain using mathematical operators called transforms. There are many kind of transformations that does do this. Some of them given below: Fourier series, Fourier transform, Laplace transform, and jet transform. So these are the four types: Fourier series, Fourier transform, Laplace transform, and jet transform are the four types are there. So these are the transformation techniques. So what is a major thing is that a signal can be converted from time domain into the frequency domain using mathematical operators called the transformation. There are many kind of transformations of this. So time domain is converting into the frequency domain. If I am taking the image of x-axis and y-axis, okay, mostly we are taking it is a time and it is a some frequency or anything, some pixels like this. But here, when I'm going to the frequency domain, this time domain I'm taking as a frequency domain. So in that converting to the time domain into the frequency domain, there are the four types are there: Fourier series, Fourier transform, Laplace transform, and jet transform. Okay, each one what are the advantages and what are the applications we'll discuss later. Here the input signal is a cosine wave, and what is the input signal? It is a cosine wave, that is a signal of S of t. So what is the Fourier transform for this one? Okay, so the output is a Fourier transform. So it is the input, I have to convert into the Fourier transform. So it is I'm taking as a output. So for the input, what is the output? It is the output. If I'm taking sinc function, it is a uniform band of frequencies. Gaussian, it is a Gaussian, and it is a double exponential. It is a logarithm. Okay, so these are the four types of input signals, that is S of t, and four types of Fourier transform, that is the output signals S of omega. So the cosine wave is input signal, and what is the output? It is a single frequency. It is like this. And the sinc functions or sine function, it is a uniform band frequencies, and a Gaussian function, and a double exponential. Okay, these are the four input signal functions are converting to the Fourier transform of S of omega. So it is one example. Suppose I am taking two input functions, that is a 3000 Hz and 5000 Hz are the inputs, and I am converting to the these signals are converting to the output. So it is a converting to the sound value, but that means I am converting to the time domain. So this time domain I am converting into the frequency domain. So what is the use of Fourier transform means? Here I am converting to the time is converting to the frequency. So here input is a time domain signal, I am converting to the frequency domain. So time domain is converting to the frequency domain. How it is possible means, here I am using Fourier transform. I am applying the Fourier transform here. So what is the input here? So 3000 and 5000 are I am giving the input values. So for this 3000 and 5000, what is the frequency? That the frequencies are like this. For 3000 it is like this. For 5000 it is like this. So these are different levels are there. It is a first level and it is a second level. So that is a spectrum strength. So it is a spectrum strength. So it is a frequency domain and a time domain. Inputs are 3000 Hz and 5000 Hz. It is a time domain. When I am going to the frequency domain, the 3000 and 5000 Hz levels are like this. Okay, when I am applying the Fourier transform. Next, Fourier series. Fourier series simply states that it is a periodic signals can be represented into sum of sines and cosines when multiplied with a certain weight. In further stage, the periodic signals can be broken down into further signals with the following properties. The signals are sine and cosine. The signals are harmonics of each other. So, what is the Fourier series? In the previous slide, we discussed Fourier transform. So, now I am discussing Fourier series. So, it is simply states that it is a periodic signal that can be represented in the sum of sines and cosines when multiplied with a certain weight. It further states that periodic signals can be broken down into further signals with the following properties. So, the signals are sine and cosine. So, the signals are harmonics of each other. These are the Fourier series and Fourier transform. The Fourier transform simply states that the non-periodic, see here it is a non-periodic signals whose area under the curve is finite can also be represented into the integrals of the sine and cosine after being multiplied by a certain weight. So the Fourier transform has many wide applications that include image compression and JPEG compression, filtering and image analysis. If the images are non-periodic, so Fourier transforms are used to converting them into the frequency domain. So what is the use of Fourier transform means? Time domain is converting to the frequency domain. How it is possible means it is a Fourier transform is used to converting them into the frequency domain. So the Fourier transform has many wide applications include image compression, that is a JPEG compression, filtering and image analysis. These are the applications of Fourier transform. So the Fourier transform is an important image processing tool which is used to decompose an image into its sine and cosine components. The Fourier transform is used in a wide range of applications such as image analysis, image filtering, image reconstruction and image compression. So the Fourier series and Fourier transform to convert a signal into the frequency domain. Signal is converting to the frequency domain. Time into the frequency, or already we discussed here, the signal is converting to the Fourier transform or Fourier series. So the input signal S of t is converting to the Fourier transform S of omega or Fourier series. These are the advantages of Fourier transform and Fourier series. So the Fourier transform is an important image processing tool. So why I am taking it is an important means it is the sine and cosine components of the input images. The Fourier transform is converting to the image analysis, filtering and image reconstruction and the image compression. So these are the applications of Fourier transform and Fourier series. So Fourier transform and Fourier series are converting the signal into the frequency domain. So what are the differences between spatial domain and frequency domain? So the spatial domain, we deal with the images it is and the value of the pixels of the image change with respect to the scene. Whereas in frequency domain, we deal with the rate at which the pixels values are changing in spatial domain. So spatial and the frequency domain. What are the differences of spatial domain and frequency domain? Spatial domain, frequency domain. So a spatial domain, we deal with images as it is. The value of the pixels of the image change with respect to scene. Whereas the frequency domain, we deal with the rate at which the pixel values are changing in spatial domain. Okay, here pixel values are changed. So in spatial domain, pixel values are changed, and in the frequency domain, we are converting to the Fourier. We are using Fourier transform, and we are converting into the frequency domain. We are converting to the image compression like this. So the frequency domain, we deal with the rate at which the pixel values are changing. Rate of change in pixels. that is the frequency domain. And filters, what are the major roles of filters in the image processing? So the concept of filter in frequency domain is same as the concept of a mask in convolution. After converting an image to the frequency domain, some filters are applied in filter process to perform different kind of processings on an image. The processing include blurring an image, sharpening an image, etc. So the common type of filters for these purposes are ideal high pass filter, ideal low pass filter, Gaussian high pass filter, Gaussian low pass filter. So these are the four types are using in the filters. So the filter is a frequency domain in the same concept of mask in convolution. So it is nothing but a mask. The mask technique is using in the filters. So after converting an image to frequency domain, some filters are applied in filtering process to perform different kind of processing of an image. The processing include blurring an image, sharpening of image, etc. So what are the common types of filters are there? Ideal high pass filter, ideal low pass filter, Gaussian high pass filter, and Gaussian low pass filter. These are the four types of filters are using. And what are the frequency components are there? Any image in spatial domain can be represented in a frequency domain. But what to do in these frequencies actually mean? We will divide frequency components into two major components, high frequency components and low frequency components. So any image in the spatial domain can be represented in the frequency domain, but the frequencies actually mean we will divide frequency components into the two major components. So what is the high frequency components? High frequency components correspond to the edges of an image, and the low frequency components are the images correspond to the smoothing regions. So in the above signal, the last signal is actually the sum of all the above signals. This was idea of the Fourier transform. So these are the input images with the different waveforms. These are sum of all here, sum of all signals. Okay, that is the advantage of Fourier series. How it is calculated, the Fourier series or Fourier transform? So the frequency domain in that is in the order of processing of an image in frequency domain. We need to first convert it using into frequency domain, and we have to take inverse of the output to convert it back into the spatial domain. And the both Fourier series and Fourier transform has two formulas, one for conversion and another for converting it back into the spatial domain. Okay, so Fourier series and Fourier transform two formulas. Okay, there are two different formulas, one for conversion and another for converting. The Fourier transform is for converting back. So conversion of spatial into the okay. So here the Fourier series are conversion of spatial to the frequency domain. Here Fourier transform is for frequency domain into the spatial domain. So these are the advantages of Fourier series and Fourier transform. So what are the properties of Fourier transform? Separability, translation, rotation, periodicity and complex conjugate, rotation, distributivity property, scaling and convolution. These are the properties of Fourier transform. So separability, translation, rotation, periodicity and complex conjugate and rotation, distributivity property and scaling function and convolution function. These are the properties of Fourier transform. So separability property, f of x comma y equal to capital F of u comma v. So here it is I am using 2D transform dividing into the 1D transform. Okay. So 2-dimensional of image is converted to the 1-dimensional of image. That is the separability. And the translation property, small f of x comma y equal to capital F of u comma y, and f of x comma y is a Fourier transform of capital F of u comma y. It is a Fourier transform of f of x comma y. It is a translation property. So periodicity and complex conjugate. Fourier transform of f of x comma y equal to capital F of u comma v. But here capital F of u comma v equal to capital F of u plus n comma v plus n. So here small f of x comma y is a real function, and we are applying the Fourier transform to the small f of x comma y. I am getting the capital F of u comma v. So that is a periodicity of complex conjugate. So what is a rotation? F of x comma v equal to capital F of u comma v. But here x comma y minus r comma theta. Here I am using rotation property, theta plus theta naught r comma and capital F of r comma theta plus theta naught. It is a rotation. And a distributive property. So I am using two functions, capital F of small f of f1 of x comma y plus f2 of x comma y. So in the frequency domain, a digital image is converting from spatial domain into the frequency domain. But the frequency domain, the image filtering is used for image enhancement for a specific application. A fast Fourier transform is a tool of the frequency domain used to convert the spatial domain to the frequency domain. The frequency domain represents of a signal allows you to observe several characteristics of the signal that are either not easy to see or not visible to all when you look at the signal into the time domain. For instance, frequency domain analysis becomes useful when we are cyclic behavior of a signal. So here we are discussing majorly Fourier transform, Fourier series and fast Fourier transform. But here the frequency domain, it is a digital image converting to the spatial into the frequency. But the frequency domain image filtering is used for image enhancement for a specific application. A fast Fourier transform is a Fourier transform in the tool of the frequency domain used to convert into the spatial domain to the frequency domain. But the frequency domain represents of a signal allows you to observe several characteristics of the signal that are either not easy to see. But where instance of frequency domain analysis, it becomes useful when we are using a cyclic behavior of a signal. Here the introduction of the frequency domain. Here I am taking one input image. It is converting to the frequency distribution and it is processing, that is the image processing. Image processing means Fourier transform, Fourier series, fast Fourier transform. These are the transformation techniques are applying in the processing. So after this inverse transform, it is the output. Inverse transform means inverse Fourier transform, inverse Fourier series, inverse fast Fourier transform, like this. So after the image processing, it is exactly inverse means exactly opposite to the processing and it is the output. So input is image and output is also image. But meanwhile what is happening means here input image I am applying the frequency distribution. When I am applying the frequency distribution means it is a Fourier transform, Fourier series or fast Fourier transform. These are the techniques of applying for the processing technique and it is a inverse transform. So inverse transform means after the processing of the Fourier transform we are giving inverse for that one. So output finally we are getting the output image. So here input and output are same, but what is the difference means here input image is converting to the time domain into the frequency domain. Then again where frequency domain is converting to the time domain. So already we know that the frequency to here I'm using Fourier series. Here I'm taking Fourier transform. Okay. Here one example of spatial domain, and output is a frequency domain. What is for process we are applying means Fourier transform. Here applying the Fourier transform for spatial domain into the frequency domain. Okay. So here f of x comma y is the input image processing Fourier transform. What is the processing means here? I am applying the Fourier transform. It is a filter function or mask technique applying here, and inverse Fourier transform post processing. So inverse for Fourier transform, we are inversing means inverse Fourier transform for this one. It is a post processing g of x comma y. It is a output image. Okay. So input and output are there. In between the input and output, what is happening means here applying Fourier transform, applying mask technique, that is a filter function. Inverse means we are inversing the here spatial to the frequency, here frequency into the spatial domain. So output is a g of x comma y. It is the output image. So the two-dimensional Fourier transform can be generated to higher dimensions. For example, many signals are functions of 2D space defined over an x comma y plane. Two-dimensional transformations are 4 different forms of depending, where the 2D signals are periodic and discrete. The first Fourier transform is an algorithm that computes the discrete Fourier transform of a sequence into the inverse transform, that is the IDFT. So here some separability functions f of x comma y equal to f of x into g of y. So two functions, here only one function, here I am taking two functions, that is a separability. F of x comma y equal to h of x comma y, h of x into g of y, f of u comma equal to h of u into g of v. So frequency domain filters are used for smoothing and sharpening of image by removal of high or low frequency component. Sometimes it is possible of removal of very high and very low frequencies, and frequency domain filters are different from spatial domain filters, basically focuses on the frequency of the images. Okay, majorly I am taking here frequency domain filters. These are the smoothing and sharpening of the image for the removal of high or low frequency components. Sometimes it is possible of removal of very high and very low frequencies. So frequency domain filters are different from spatial filters and basically focus on the frequency. So frequency domain filters are two types. So in the spatial filter, there are two types are there: smoothing spatial filter and sharpening spatial filter. In the frequency domain also two types are there: smoothing frequency filters and sharpening frequency filters. These are the two types are there for the frequency domain. Okay, so frequency domain filters are the smoothing and sharpening of the image by removal of high or low frequency components. So where I am using means it is a removal of high or low frequencies of the components. Sometimes it is possible of removal of very high and very low frequencies. So frequency domain filters are different from spatial domain filters, and these are all basically focuses on the frequencies of the images. So frequency domain filters are low pass filter, high pass filter, and band pass filter. Okay, so low pass filter and high pass filter. So what is the low pass filter means? Low frequency images are convolution of original image into the 2D Gaussian. High frequency images are obtaining by subtracting the low frequency convolution from the original image, and the high frequency images are shifted to account for negative values that are result for the subtraction. Okay, majorly we are using low pass filter and high pass filter, but very rare conditions we are using band pass filters. Okay, so frequency domain filters are low pass filters high pass filters, and band pass filters. These are the classifications of frequency domain filters. Okay, so low frequencies of the original image and high frequencies are the subtraction of low frequencies, and high frequencies are shifted to the account of negative values result from subtraction. Okay, so these are the types of frequency fast Fourier transform and the frequency signals, frequency domain filters. So these frequency domain filters are majorly using two types. These are three types, but majorly using two types. That is the smoothing and the sharpening of the filters. Okay, so these are the types of frequency domain filters. But smoothing and sharpening are majorly using for removal of high or low frequency components. But these are the possibility of removal of very high and very low frequencies. But the frequency domain filters are different from spatial domain filters, and these are basically focuses on the frequency of the images. So in this we are discussed only majorly Fourier transform, Fourier series, fast Fourier transform. These are all using for spatial into the frequency domain into the spatial domain. So majorly we are using what are the advantages of frequency domain, what are the types of frequency domains we discussed here. In the next we are discussing smoothing and sharpening filters which are using in the frequency domain. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.